So today's video is going to focus on a concept referred to as direct variation. Now, direct variation, and I'm not quite sure why we have the different terminology for it, but direct variation is essentially the same as proportionality. Okay, so when we talk about direct variation, we're talking about proportional relationships. So everything we know about proportional relationships is going to hold true when it comes to direct variation. So that being said, we should already see that proportionality is present in terms of, proportionality is present in terms of what we see for a formula for representing direct variation, because I've seen this formula already, y equals kx. And we already know that we already know that k is our constant of proportionality. But now we're just simply going to refer to it as our constant of variation. So again, guess what? Constant of proportionality and constant of variation are one and the same. So when we talk about constant of variation, we're talking about constant of proportionality. And it serves the same exact purpose. So if I know something is proportional, I also know it represents direct variation, and the same formula holds true for solving for k. So it's just that the presentation of the material is going to be a little bit different from what we've seen for proportional relationships already. Proportional relationships, we've seen data presented as ordered pairs, as tables of input and output data, as graphed data, okay, and also as equivalent ratios. With direct variation, we actually see a phrase in which one variable varies directly to the other. Okay, so all of this is going to look very, very, very familiar to us. All of this y equals kx and solving for k and ultimately writing the equation is all going to be exactly what we just covered in the last lesson. So let's see what's different about it. Well, as I mentioned, the language is going to be different. We're going to have to start with the fact that generally with direct variation, we're going to see this phrase that says y varies directly with or directly to x. And that's just the same as saying y is proportional to x. Okay, so if I know that already, then I can solve for my constant of variation. Remember, my constant of variation is nothing more than my constant of proportionality. And I already know that constant of variation, otherwise known as my constant of proportionality, is simply made up of the ratio of y over x. So if I have a y value given to me in this scenario, where it says y varies directly to x when y is 3 and x is 27, I simply set that up as a ratio. In being consistent, we're not going to solve this out as a decimal. We're just simply going to reduce it and leaving a fraction form. So my k value, is not 1/27th, it's 1/9. Is 1/9. Okay, so that's as straightforward as it gets. So don't let this constant of variation throw you off. That's our k value, otherwise known as once again, our constant of proportionality. Okay, so treat them as identical problems. So that said, I will leave you to solve the second problem on your own. You have number 1 to the right as a model for you. So when it moves on to ask us to write an equation, this is the same as when we had a proportional relationship. We have an x value, we have a y value. So the first thing we want to do is to start out by solving for k. So one more time, k is equal to y over x. And in this case, that's equal to my y value of 15 over my x value of 3. And this I can simplify. And when I move on to now transferring that information into an equation, I know I have y equals my k value, what I've just solved for, x. So I'm simply going to take my 5. I'm going to take my 5. I'm going to replace it with, or I'm going to replace my k with it. So by the time I am done, I've solved for k, my constant of variation, y equals 5x. So remember, I warned about this in class before. Solving for k, solving for the constant of variation, is just solving for that value we will need from which to build our equation from, so that if we're asked to solve for our equation, here's the complete equation. So once again, I've solved number 3 for you. I'll ask you to do number 4 on your own, modeling after number 3 as you need to. Don't leave decimals. Don't forget, convert this to a rational number, meaning a fraction or an integer as needed, okay, when writing your equation. I'll skip this group of problems, numbers 5 through 7, just for a quick moment, because I think what's easier for us to review is telling whether a graph represents direct variation. And once again, if we're talking about direct variation, we're talking about the same as proportionality. So AKA, we're talking about proportionality. Now, we already know what we need to have something proportional. It needs to be linear if we're looking at a graph, and passing through the origin. So we're going to apply those same tests for these graphs. So is this linear? It is. Does it pass through the origin? Yes. So it is direct variation. And I'll leave, once again, these next 2 graphs for you to figure out using the same test as we use for proportionality for determining if something is direct variation. So all of that is well within our comfort zone, which leaves us to quickly go back and review or answer questions like numbers 5, 6, or 7, okay? So if we are going to be direct variation, if we are going to represent direct variation, it has to take on the form of that y equals kx, again, just like it would for a proportional relationship. So my equation has to look like that. Y equals some coefficient times x, and nothing more being added or subtracted beyond the x term. So if my equation does not look like that already, then I'm going to need to convert accordingly, okay? So the first one, we may get a little bit confused because I don't see a coefficient in front of x, but if I needed to see that coefficient, I know it would be 1. And that would be my k value, and that would certainly look like y equals kx, wouldn't it? Y equals 1x, my k value being 1. So yes, that's direct variation, otherwise known as proportional or proportionality. The second one I want to get solved, so it says y equals. Now this is a lot like what we did with our literal equation. So solve this equation for y. So subtract 3 on both sides. Lead with the variable term, and you will get y equals 3x minus 3. Does that look like y equals kx? It starts out looking like y equals kx, but then we have this minus 3, and that is what presents the problem to us. So that breaks the rules for it being direct variation. So that's a no. So one more time, you have an example in number 6 in particular to work off of. Look at number 7. Convert the equation to see if it meets this template of y equals kx, and then simply answer yes that it is direct variation, or otherwise no that it does not. So to sum up, direct variation, just a fancy name or another name for proportional relationships or proportionality. Y equals kx is still a formula that applies for representing the equation. K is still the value that we use, and instead of calling it a constant of proportionality, we now call it a constant of variation. So it still plays the role of that coefficient in front of x in our equation. And that's all that there is to direct variation. So wrap up whatever is left on these notes. We'll come back to class and we will discuss more.